Hello, welcome to Notes on Characteristics of Quadratics from Any Form. This is part 2. Miss White had a video where she went into a little bit more detail on completing the square and working with different forms, standard form, vertex form of these quadratics. On this set of notes, we're going to pay more careful attention to increasing and decreasing features on a quadratic, but how they look on a graph is essential to understanding what's going on as well. So if you could make this chart on your set of notes, it's going to help us describe how to look at curves of graphs, and this will be applicable to polynomials here in the future. So increasing pieces of graphs, when they are facing up, look like this. In calculus, you'll learn a term called concavity, like concave, and this is facing up, so it's concave up. And if we're decreasing when this quadratic is facing up, then we'll be going down. So you can see that increasing is going from left to right, up and to the right, and decreasing is down and to the right. So you can write out these words if you need to. You're always referencing from left to right. And when a parabola is facing down, an increasing part of the graph is the left side. So it's coming from negative infinity and going up to the maximum. So if it's facing down and decreasing, it's starting from the maximum and decreasing to negative infinity. So increasing would be up and to the right again, and decreasing is down and to the right. We just have a different curve, a different concavity, concave up or concave down, facing up or facing down. For these graphs, maybe you want to label, maybe you do want to use colors and label the shapes themselves over here on the left, just to show the movement of increasing and decreasing. It can be a little awkward looking at it, but you're always moving from left to right, so you can kind of see that cycle if you pay a little bit of attention over here. Right, so in Miss White's notes, she had these two quadratics after you completed the square. And completing the square was the tough part, but for intervals of increase and decrease and the range, that's just boils down to the vertex. So our vertex for number 2 here, HK, is -1, -5. And I can see that because I know that that's H and that's K, -1 and -5. And then I also know that this graph is facing up. So if we're facing up, I know which half of the parabola is going to be increasing and which half is going to be decreasing. I also know what my range is going to be, because I'm going to start at the y value. The y value is my bottom, the bottom of my range. So my range is going to be -5 included, and then towards infinity, because I'm looking at my a value again. My a value is telling me I'm facing up, so I know that I'm going to infinity. And then if I'm increasing, that means I'm increasing from my x value of my vertex, -1 to infinity, and not including -1, because you cannot increase or decrease at a vertex. So that means I must be decreasing from -infinity to -1. So, and that's all from looking at the vertex. If you have to reassure yourself with a little graph, I don't think that's a bad idea. I just say it's really not necessary to plug all this into your calculator. It's much easier to double check the vertex, and then maybe sketching a small graph would be faster instead of just like trying to remember which side you're looking on. So here's -1, -5, and I'm increasing on this side, so that's this, decreasing on this side. So that's -1 to negative infinity to -1. All right, and then my range is represented, of course, with the closed circle all the way to infinity. All right, and then this other one, we'll run through it pretty quickly. H is 3, 4, but we are facing down. So we're going to be increasing on the left side of our maximum, because we have a maximum in this graph. It looks like this if it's facing down. So our range, the y value is now the top of our range. So our range is going to be negative infinity to -4 included. And it'll be increasing from negative infinity to our x value, 3, not including 3, and then decreasing 3 to infinity. Notice that these intervals are x. This interval is, of course, a y interval. And that's all because we know what we're being asked is a range, those are y values, and increasing and decreasing intervals are always x values. For number 4 and 5, I altered, well, I should say I altered 3 as well. I just changed the 2 to a -2, just so we'd have some variability. And I altered number 5 as well. So make sure you get that change. With these two, we do not have a lovely vertex form. So I'm going to ask you to go ahead and get these in vertex form, and we'll reconvene once they are. On 4 and 5, the vertex forms are listed below. Here's H on each and K on each. So my range for the first one, this quadratic is facing up, the parabola is facing up. So my range is -225 over 4 to infinity, with that number included. The interval of increase is the right side of the parabola, so it's -19 over 2 to infinity, and then it's decreasing from negative infinity to -19 divided by 2. The range on number 5 is going to start with negative infinity and go to positive 28, including 28, because this is a facing down parabola. Remember, I changed this one just a little bit. And the interval of increase is going to be on the left side of this downward facing parabola. So negative infinity to -3, not including -3, and then it's decreasing from -3 to infinity. Great. And a quick note on simplifying radicals, because I know it comes up when solving for x-intercepts. This is a typical result from the quadratic formula, or maybe from using a complete the square problem to solve. When working with the radical, remember you are looking for factors of 72, and you're looking for the greatest common factor of the greatest factor of 72 that is also a perfect square. So in 72 we have 9, we've got 36, and 36 is actually the largest perfect square. So you can write those numbers like that. If you get stuck and you only do 9, so you have 9 times 8, then you can still get to this end result. You're going to split the radical, because a radical is just a power, so you're actually doing a power to a power here. So this is 6 radical 2, and then for 9 times 8, you can split 8 again, so you'll have radical 9 times radical 4 times radical 2, and radical 9 is 3, radical 4 is 2, and radical 2 is there. So I end up in the same spot. And when you're simplifying this complex fraction, remember to divide 8 and 6 by -4. So I'll get -2 plus or minus 3 radical 2 over 2. Very cool. So that's the end of our notes. Look forward to seeing you guys later. Bye.